Greetings everyone. One of the components that I need in my 10 GHz tower-mounted system is a combined 144 MHz transfer switch and 33 dB attenuator. That's for the IF in and out, so transmit and receive. So I've completed the design, assembly and test of my unit, and it's working really great. Now, in order for you to understand exactly what it's about, let's go see the schematic diagram. So here it is, the schematic of my transfer relay / attenuator. Basically, it's either a direct path going through when we're in receive, so we don't want to attenuate in receive. When we're in transmit, we want to take half a watt from the IF radio, 144 megahertz, in my case it's going to be the IC705, half a watt, and attenuate it through a pi attenuator. And in order to be safe, I've decided to use a non-inductive power resistor, the same I used in my previous design for my portable 10 gig system. It's a 50 ohm, 60 watt non-inductive resistor. 60 watt, I have big question marks about this considering the size. But in any case, for half a watt or a few watts, it's perfect. You'll see how it gets soldered down onto the board when I show you the final implementation. And then it's a pi attenuator. So this resistor here, to get to 33 dB, which is what I need. 33 dB means 1116 ohms-ish, roughly. I got to 1120 with two resistors mounted in piggyback, one over the other, so in parallel basically. 1.21K in parallel with 15K gives me 1120, which is close enough. And a 51 ohm resistor on the low power side. These are 1206 resistors. It's a surface mount design I've decided to do this time, except maybe for the LED. And yeah, so these are the two paths, straight or attenuated. In order to switch from one to the other, I have these two relays. They're in series because it's the 5 volt version. 5 volt plus 5 volt for the two coils makes it to 10 volts, and 8 to 10 volts is sufficient to switch the two relays. Actually, it will switch with 75% of the voltage according to the data sheet. So 8 volts, which is 80% of the 10 volts, will work fine to switch the two relays. So we switch into receive and leave it alone into transmit. So by default, it's on the attenuator portion to preserve the transverter of any high power that would come in a non-desired way, of course. And only when we're ready to receive, we switch the relays on, and this will open the path, a straight through path for the receive from the transverter to the IF radio. Now I've also added, and I did the same in my previous design, microwave diodes, which I had in stock, so it cost me nothing. These are just to clamp a high power situation. I don't know how much power they can take without blowing up. Past a certain point, a certain voltage, these will clamp and try to protect the receive path in case there is some high power going through the receive path, which is not supposed to happen. But hey, I had those resistors. Worst case, they just burn, they blow up, and then they don't serve any purpose. At 144 megahertz, they don't affect the VSWR here in a meaningful way. And for the coils, I've also added some clamping diodes to absorb the back EMF. So they're in reverse bias by default. But of course, when you cut off the supply, they will clamp the back EMF, which goes negative. And that's why we have these diodes here. I now also added, as I mentioned, an LED to show that the thing is in receive, so powered up. Now to come back to the relays, these are RF relays. They're not regular like power or signal relays. They're called RF relays. Why? Well, they can work up to 3 gigahertz with very decent performance. Their isolation between the contacts is 60 dB up to 1.5 gigahertz and proportionally less as we reach 3 gigahertz. Regular relays I've tried, you can get around 30, 35 dB. That's the maximum isolation that you can get. In my case, with a 33 dB attenuator, it would likely have worked with regular signal relays, but I decided still to look for good RF relays, and I found these Omron G6Z-1F-A, which is a 50 ohm version. These are single pole double throw, so they're not latched. You need to energize the coil to switch from one side to the other, and then when you release the power, it comes back to the normally closed position. So it's a regular one-pole relay, two sides, and as you notice, there are lots of ground pins, which help for, of course, maintaining 50 ohm impedance inside the relay. So it's a good design of relay. Unfortunately, it's not cheap, and I'll mention something in a couple of minutes about it. So here's the implementation that I did. I designed these PCBs based on the schematic, of course. I designed the layout, and it's dual-sided, and I have some 144 megahertz tracks on both sides of the board. The relays are both on the same side, and they're more or less face-to-face, as you can see. And this is the attenuator path, and this is the through path that you see here on the bottom side. And the paths are 50 ohm impedance, coplanar waveguide on both sides. Thickness is half of what you normally see for a PCB, so 31 mils thick. So that's regular PCB material, FR4, 144 megahertz, it works great. This is designed to custom fit this enclosure. I have a few of these left, so I don't hesitate to design a board based on these dimensions. The connectors I decided to use were BNCs at 144 megahertz, and they're BNCs with SMA PCB footprint. As you look, this is a classic SMA footprint, 5-pin with the center conductor, 4 grounds, and they're just drop-in replacements BNCs. So I like them a lot. I have another set of 2. These are recovered from I don't recall what, and I had issues finding these connectors. I'm sure they exist. One manufacturer for sure makes them. I just couldn't find a reference, but they're too nice to just not use. So yeah, BNCs. I could go to SMAs if I wanted to, if I really wanted to. And here I had to make notches. This is actually version 2 of the board. The first version I had a few mistakes. The biggest one was wrong pin out for the relays. The relays have several versions available, and those that I got didn't match the design that I saw in the datasheet. Okay, talking about relays, I mentioned to you these are RF relays, and you can have a look at them. They're not standard single relay. They're sealed from what I can see. There is some epoxy. The black part is epoxy. The white part looks like ceramic. The case is plastic, but it's really hard plastic and not easy to melt. You look at the pins, it's surface mount. They're short, and they have ground pins on either side of single pins. So this is the common point here. And this is one of the points, like normally open, normally close, and the other one. And yeah, there are grounds everywhere, and the coil is over here. These relays, they sell for more than $20 a piece. If you look at, for example, DigiKey. I decided to buy these relays, the ones that I used from AliExpress. They were around $3 delivery included per relay for a set of relay. So I bought 6, if I recall. And I was a bit disappointed to see that they were not new, because they were advertised as being new, and no, they're not. They were reused, so pulls. And the pins were really hard to solder to. They actually would not solder well with regular solder, even with flux. I don't know what design they were used on and what type of solder they used and how they got removed, but there was like some oxidation on the pins, so I had to scrape off with a small X-Acto knife, scrape off the surface of all pins, both sides, and managed to solder them in place. It worked this time, though it's still not perfect, as good as I would like for every single pin, but it's okay now. It's soldered. At least the bottom side is soldered to the board, which is what matters really. So yeah, the attenuator, this is the 50 ohm 60 watt termination resistor. It's soldered in place very well with a lot of heat, and I ended up soldering the other contact at the end, obviously. And I doubt that it can take 60 watts, but it can take several watts. But actually, I'm only sending about 500 milliwatts into this thing. It's just in case I send 5 watts by mistake. If the IC705 is not set to 500 milliwatts, there's a risk, you know, if I used regular small resistors, I could have blown them up, whereas with this guy, it won't happen. And the rest of the pi attenuator is on the opposite side. The 2 piggyback resistors, like you saw in the schematic, and the other 50 ohm resistor here to complete the pi attenuator, and then out to the transverter. So I did install an LED, of course, that will show that the thing is powered up. By default, like you saw in the schematic, in the resting position, the attenuator is in line, just to preserve the transverter just in case. And then to receive a signal on 144, so in receive mode, it's the relays that get turned on and they conduct the bypass path, this guy here. Then it's a straight through minus a little bit of attenuation. On the IF signal, there's no lack of gain. It's not an issue even if you add a bit of attenuation. It's not 0 dB, but who cares? We got plenty of noise, plenty of signal on the receive path. On the transmit path, of course, it's not critical. We can compensate for the losses, if any, on the transmit path by sending a bit more RF power. And don't forget, there's a lot of coax between this guy and the radio in the shack. So I may have to go to 600 or 700 milliwatts instead of 500 milliwatts to compensate for the losses in the coax. There's going to be around 60 feet or like 18 meters or 19 meters of coax plus this. So yeah, to get the full 12 watts output at 10 gigahertz, I'll have to adjust depending on the coax length. I did add a feed-through capacitor for the supply, the 8 volt supply going in. It's a good practice to add these. It filters anything that could go out or go in at those frequencies. No problem. Okay, so that's it for this transfer switch. On to the next part. 7.3.